Today we start an important topics related to measure theory. Okay, so we discuss today LP space. LP space. Okay, that means alpha integral space. Okay, now we also going to discussion of something. Here we know about that mu a to 0 infinity some measure. Okay, and obviously we know about that this r equal to what, minus infinity to plus infinity, and c equal to what, r plus ir. Okay, and then what happened, c closure equal to what, r closure plus ir closure. Okay, and r closure equal to what, r closure equal to closed minus infinity to plus infinity closed. Okay, so I understand about that. I think all are understand. So now we erase that portion and going to further discussion of definition of measure. Okay, we known about in previous class, but we also discuss today just definition of measure. Okay, so let x a this algebra be a measure space, be a measurable space. Okay, then what happened, and mu this collection a to 0 infinity 0 plus infinity be a set function, okay, some positive valued functions, that means some 0 and positive valued functions, we call it set function. Okay, and then what happened, then mu is said to be measure when if first one mu phi equal to 0 and second condition is mu is countably additive, mu be if measure, then this one is, that means sigma finite not needed here, just measure, so countably additive. Okay, countably additive means what, that means there exists mu of union n equal to 1 to infinity a n equal to summation n equal to 1 to infinity mu of a n. Okay, then we also, that means this one is the definition of measure we also discussed today. Now we erase that portion and going to further discussion of some outer measure. Okay, some outer measure, we write it now, outer measure, and going to discussion about that outer measure. Let I be an open interval, I be an open interval in R, and Li denote the length of I, and E subset of R, then the outer measure of E, is denoted and defined by mu star E equal to here infimum of summation n equal to 1 to infinity, okay, L of in, here E subset of union of n equal to 1 to infinity in, and and in is an open interval in R. In is an open interval in R. Okay. So then mu star that means satisfies some properties. We erase that portion and going to further discussion of that. Okay, this one. Then mu star VR to 0 plus infinity, which has the following properties, which has the following properties. Okay, first one, mu star phi equal to 0. Second one, okay, mu star be monotone. That is a subset of B implies that mu star A less than equal to mu star B. Okay. Number 3, mu star B countably subadditive. Okay. Then mu star be an outer measure on PR. Then mu star be an outer measure on PR. Okay. Now we erase that portion and going to further discussion of that. That means some measurable set. Okay. Some measurable set or Livek measure set. Livek measurable set. Okay. Let E be a subset of R and the outer measure of E, okay, is denoted and defined by mu star E equal to mu star E intersection A plus mu star E and E complement intersection A. Okay, for all A subset of R. Such E is called Livek measure set. Livek measurable MEA measurable set. Okay, or mu star measurable set. Then again we also erase that portion and going to further discussion of that. some observation. Okay, let M be the collection of, let M be the collection of Leibniz measurable set, Leibniz measurable set. Okay, sets. Then what happened? Then phi x belongs to this M. And second, if E belongs to M, implies that E complement belongs to M. Third, En in M, then union of n equal to 1 to infinity En belongs to M. Okay, so M is a sigma algebra. Okay, then we erase that portion and going to further discussion of that. Now here we also discuss about that measurable function. Okay, measurable function. Then what happened here? Here we know about that. Let E belongs to M. Okay, and A be a function and A be a function if E to 0 infinity. Okay, sorry, here minus infinity to infinity. Okay, sum. Then F is said to be, then F is said to be, okay, F is said to be measurable if this one E superset of EF greater than A. Okay, that is those x such that x belongs to E such that if x greater than A. Okay, for all A belongs to R. Then obviously here E if greater than A belongs to M. Okay, be measurable. Now if E to C is measurable, now if E to C be measurable, if it's real and imaginary parts is measurable, and imaginary parts be measurable. Okay, then we also erase that portion and going to further discussion of that. Here we know about that characteristics function. Okay, characteristic function. Which functions is called characteristics function? Those we write it denoted by this one, psi ex equal to here 1 if x belongs to E and 0 if x does not belongs to E. Okay, then we write it now simple function. Simple function here phi e2 minus infinity plus infinity is simple be simple if phi x equal to summation I equal to 1 to n ai and here psi ei x. Okay, where ai belongs to R and what happened, and ei intersection ej intersection ej equal to phi. Okay, then phi is some linear combination of characteristics function. Then phi be linear combination of characteristics function. Now integrability of measurable function. Okay, we also discuss here, that means some integrability of measurable functions. Let phi e to 0 infinity closed be a simple function. Be a simple function okay. We also discuss about simple function, that means some linear combination of characteristics function. Okay, simple functions, then the integral of phi, over e b integration of phi d mu over e equal to summation ai mu ei. Okay, I equal to 1 to n. Okay, then next we write some definition here. In this way we write here, let e belongs to this measurable function. Okay, and if e to 0 infinity be a measurable function. Be a measurable function. Then integral of f over e is integration phi d mu equal to over e equal to what? Sorry, integration f d mu. Okay. F d mu equal to supremum of those phi d mu over e such that phi e to 0 infinity be a simple function. Be a simple function such that 0 less than equal to phi less than equal to f. Okay, so now erase that portion and going to further discussion of that. Okay, that means how integrability of measure function we discussed now. Okay, now we're going to another discussion. Here let e belongs to m, some measurable set, and if e to here minus infinity to plus infinity be a measurable functions. Be a measurable function. Define f plus equal to define f plus x equal to what happened maximum of fx0 and f minus x equal to here minimum of minus fx0. Okay, then what happened? Then mod f equal to f plus plus f minus. Okay, and f equal to f plus difference f minus. Okay, then again what happened? Then integration of e f d mu equal to integration of e f plus d mu difference integration of e f minus d mu. Okay, this one belongs to minus infinity plus infinity, and integration of e mod f d mu equal to what happened? Equal to integration of e f plus d mu plus integration of e a minus d belongs to 0 plus infinity. Okay, so we define f plus f minus and obviously mod f and f equal to what, and obviously integration of f and integration of mod f equal to what we also define today. Okay, now we also going to discuss another portion, just definition of integrability. Okay, we erase that portion and some definition we discussed today. Then I stop here today. Write definition first. Okay, then I stop here today, and next day we also discuss more things. Okay, so we write this definition here. Let e belongs to m. Let e belongs to this measurable set, and if e2 are closer, be a measurable functions, be a measurable function. Okay, then what happened? Then first, f is said to be integral over e if integration of mod f d mu less than plus infinity. Okay, over e, and here obviously we write in this way: if is said to be p integral, f is said to be p integral over e if integration of e f to the power p d mu less than plus infinity. Okay, and obviously this p belongs to 0 infinity. Then we also stop today. We also discussion so many definitions: definition of measure, outer measure, measurable set, measurable functions, characteristic functions, simple functions, integrability of simple function, integrability of some function over e, and obviously positive function, negative functions, modulus of functions represented by positive and negative functions, and then definition of integral and p-integral function. So today we stop here, and next day we also discuss so many topics of measure theory, okay, or LP spaces. So now we stop here, okay, and if you getting this type of videos, then please subscribe my channel, and if you obviously like this video, then gives like, and if you want to that means want to get this type of video, then obviously subscribe channel, and if you have any questions and any suggestions, then please write it in comment box. So today I stop here.